I am delighted to welcome today's speaker in our seminar, George Perrett. George is a visiting assistant professor at NYU and is the research director of the Think Causal Lab at NYU's PRIISM Center. George works on developing tools to make causal inference more accessible, expanding the capabilities of existing causal inference methods, and understanding cognition around causal inference. He has earned degrees in psychology, public health, and applied statistics. So we're delighted to have you here, George, to talk about accessible causal inference. Take it away.
All right. Well, thank you for the warm introduction, Ravi. So as Ravi said, I'm going to talk about accessible causal inference. And I want to begin by introducing an example that we're going to use today. So a well-known sports company created a high-performance marathon shoe. Now, there's a real product, but we're going to call this high-performance running shoe the Hyper Shoe. So we're going to protect the brand's identity, but this is based on a real example. And Hyper shoes were released with the claim that wearing the shoes causes runners to run a marathon 4% faster than they would have ran without wearing Hyper shoes. And so the question I want to be focusing on is, how do we know if Hyper shoes actually caused faster running? And to answer this, we're going to have to think first of, what does a causal effect mean anyway? Like, what does causality actually mean? We might have a lot of notions around it, but let's get a little bit more concrete. So this is Helen O'Beary. She was the winner of the 2023 New York City Marathon. And Helen is wearing Hyper shoes. And when we think of a causal effect, we want to compare what would have happened, or what did happen when Helen wore Hyper shoes, against what would have happened had she not worn Hyper shoes. So it's a within-person comparison. It's Helen with the shoes compared to Helen without the shoes. And we think of these things as potential outcomes. So a potential outcome is what would have happened in one world and what would have happened in this counterfactual world. And the causal effect of the shoes, which is usually denoted as tau for Helen, is just the difference between her potential outcomes. Y1 is how fast Helen would have ran with the shoes. Y0 is how fast Helen would have run without the shoes in a parallel universe where everything else was exactly the same. Now, it's easy for us to know how fast Helen ran with the shoes because we directly observed this. She ran the marathon in 2023. We see that she's wearing Hyper shoes, and we record her time of 147 minutes, which is remarkably fast. Now, some of you may be thinking, there's an obvious problem here. We actually have no way of knowing how fast Helen would have ran without the Hyper shoes. We didn't see this, and so we don't know. This problem is so large, it's called the fundamental problem of causal inference. We cannot observe what her time would have been without the Hyper shoes. Now, there's some proposed ideas when I talk about these things. People usually say, well, this isn't actually a big problem. I can think of a solution already. How can we know how fast Helen would have ran without Hyper shoes? Well, here's an idea. After she finishes the race, we could have her return to the start line and rerun the race, but this time not wearing Hyper shoes. And then we'd observe how fast she ran without the Hyper shoes. Now, the only problem with this is running back-to-back marathons would be very fatiguing. If she ran slower without Hyper shoes, it's impossible to distinguish if the change was because of the different shoes or the fatigue. So this isn't a viable solution. So if fatigue's a concern, why don't we just have her run another marathon without Hyper shoes in a few weeks or a few months after the race we observed? She'll have some time to recover, and then we'll have her rerun the race, but this time without wearing the Hyper shoes. So the problem with this is a whole bunch of other things could be different. It's possible that the weather could be different. It's possible that she changed something in her training routine, and maybe she would have ran faster regardless, or maybe she would have ran slower. It's impossible to distinguish if any change is because of the different shoes or another variable like weather or training or age. Again, this isn't a viable solution. The fundamental problem of causal inference is not a solvable problem. And these individual causal effects, the true effect of Hyper shoes for Helen, it's non-identifiable, meaning we won't be able to recover it. Fortunately for us, we can estimate average causal effects. So we might not be able to know how big of a difference the shoes made for Helen, but if we have a lot of people, if we have many, many runners, say all 150 runners in the professional women's category, we can estimate how effective the shoes were on average. And this is called an average causal effect. Now, there's many different types of average causal effects. The one I'm going to be focusing on the most today is called the sample average treatment effect. And it's just the average of y1 minus y0. Y1 is how fast a given runner would have ran with the shoes, and y0 is how fast that runner would have ran without the shoes, averaged over the whole sample. So here, n is just the number of people in our sample, in this case, 150. Now, the fundamental problem of causal inference still applies here. In the definition of state, we have both potential outcomes, and we don't observe both. We can never observe both. So what do? How do we move forward? Well, the idea is we can use the information we do observe to help impute the missing counterfactual value. So causal inference is really a missing data problem, where we're going to be imputing and filling in these missing potential outcomes for each person, and then we can take that average to estimate the state. So here I have times for each runner. We may have a pre-treatment covariate like resting heart rate, which is very predictive of running time. We have the treatment variable, z, and I'm going to be using z to represent if a runner wore the hyper shoes. That's going to be z equals 1, and z equals 0 is going to reflect that a runner did not wear the hyper shoes. Now, we're not always just interested in averages. Sometimes treatment effects work differently for different people. This is oftentimes called a heterogeneous treatment effect. A certain drug may work better for certain types of patients. In the case of hyper shoes, maybe hyper shoes have a bigger benefit for the best runners, and they don't work for slower runners. Or maybe it's the opposite. Maybe they only work for people who are slower and have a lot of room for improvement, but the fastest runners have kind of maxed out all of their capabilities. And so the Kate is a different type of average causal effect, and it's going to allow us to reflect treatment effect heterogeneity. And we'll revisit Sate and Kate later on. Now, randomized studies are often presented as the gold standard of causal inference. So optimally, we could do a randomized study on these runners to actually identify if the shoes cause them to run faster. And randomized studies combine design, which is the randomization, and statistical modeling to estimate a causal effect. And what I'm going to try to get across today is we actually need both of these pieces. There is a modeling piece of randomized studies that is oftentimes ignored. But the design piece is also critical, and it carries a lot of really useful properties. So how does this actually work? Well, let's say before beginning the 2023 New York City Marathon, the 150 professional women's runners were randomly assigned to run the race with hyper shoes or without hyper shoes. So each runner has a 0.5 probability that they're going to wear shoes. And that's the same for everybody. And before randomly assigning the treatment, the resting heart rate of each runner was reported. And this is valuable because resting heart rate is a really reliable indicator of overall fitness. And we expect the fittest runners, the runners with the best aerobic capacity, to run the fastest. And pre-treatment variables, I'm going to be using this term several times throughout, so I just want to focus on what it means now. Whenever I say a pre-treatment variable, it's any variable that's not influenced by the treatment. And we could think of that as any variable that does not have potential outcomes. Here, resting heart rate, it's a pre-treatment variable because we measured it before the treatment was even assigned. It's impossible for hypershoes to change our measurement of resting heart rate. Demographic variables are another thing that is always going to be a pre-treatment variable because we never expect the treatment to change those. There's no treatment that we know of that actually makes people younger, for example. Now, randomized studies aren't assumption-free. We're going to make a few structural assumptions. One of which is the ignorability assumption, which is that our potential outcomes, y1 and y0, are independent of the treatment. And so what does this mean? How I want people to think about it is that the treatment was actually random. Sometimes randomization doesn't work. There's a lot of reasons how that could happen. We could have differential dropout, things like that. But so we're assuming that the randomization actually holds. And if this is true, it means that there's no confounding variables or third variables, which we'll talk about a little bit later on. And an implication of this is that we can use the y1s that we have to represent the y1s that we don't have. And we can use the y0s that we have to represent the y0s that we don't have. There are some other assumptions, notably the stable unit treatment assignment. It just means that my treatment is not going to influence somebody else's outcome. But we're not going to focus on that too much today, but it does exist. So here's the data from our randomized study on hypershoes. And a really nice property of randomization is that we have balance in expectation. Now, what does balance mean? If we look across levels of resting heart rate, we have an equal amount of people in the treated group and the control group on average. And this means that all the covariates that we've measured and haven't measured have the same distribution in expectation. Now, this is only true in expectation. So if I look at the distribution of resting heart rate between people that ran with hypershoes and people that ran without hypershoes, these distributions are a little bit different. Now, if we took these to expectation, if we increase sample size to infinity, these distributions would become exactly the same. But if we look at the means right now, these means almost identical to each other. So on average, the treatment group has the same resting heart rate as the control group does. Now, before I talk about estimating these things, we're going to do something that we never can actually do as researchers, and that's try to see what would happen in this counterfactual world. So let's imagine that I have this kind of magical machine that's going to allow me to visit some parallel universe. And so this machine can take me to this parallel universe where each runner ran with the opposite shoe, and everything else was exactly the same. Now, this is not something we can ever do in real life, but as statisticians, we can use synthetic data to understand the properties of causal inference. So these data sets, I've synthetically generated them, so I actually know the true value of the sample average treatment effect. So this plot shows the factual outcomes, the things we actually can observe, showed as filled in circles, and the counterfactual values. So these are the true potential outcomes for every single observation. And so I can calculate the individual causal effect for each runner. Now, this is something I can never do in the real world, only with synthetic simulated data. And if I take the average of all of these, that's going to give me the true state. And so I'm going to write that down. We're going to hold on to it for later. And we're going to use this to see how our estimations are working. We're actually able to reliably identify this. And so the true state is negative 4.25 minutes. So hypershoes actually, on average, cause people to run 4.25 minutes faster than they would have ran without the shoes. I can also look at the true Kate. And so there's quite a bit of heterogeneity. So for faster runners, the shoe works. But once we cross some threshold around a resting heart rate of 52, 53 minutes, hypershoes actually become harmful. And we see that by the positive values over here. So these runners have a negative impact. Hypershoes are iatrogenic, meaning they cause harm to them. So how does estimation work when we've randomized the treatment? So one way to do it is we can use the difference in means. So how does the difference in means work? This is the modeling component I was talking about. We can just take the average of the data we actually observe. And we're back in the real world now, I should say. I've taken away our access to the real potential outcomes. So I can just take the mean and write down the average Y0 for all of our missing Y0s. And I can do the same thing for our missing Y1s, where I'm just going to take the average of all the Y1s we actually observe and fill it in. Now we'll see for each person, it's going to be the same. And this is a really poorly specified model. Like we can just see, we know the response surface is very nonlinear, and these lines do not fit it well at all. But that's actually okay. Because we have balance and expectation, we know there's no confounders. Our estimate from the difference in means is going to be really close to the true state. Now, calculating the uncertainty of our estimate is a little bit more complicated, so I'm not going to go into the steps to do it. But I will show you that this is our uncertainty related to the sample average treatment effect. And randomized studies are great because the difference in means is unbiased in expectation, but we don't care about in expectation. We care about the one study we actually have. So if I look at the results from this study, I'm not able to reject the null hypothesis if I'm a frequentist, that the state is equal to 0. And if I'm a Bayesian, I'm looking at this and saying, well, there's still some probability that hypershoes on average are harmful. And so we don't just care about biasness, we also care about efficiency, basically how precise can we estimate a value. So how do we get more efficient? Well, one way is we can improve our statistical model. So resting heart rate, it's a pre-treatment variable. And we're not utilizing any information about resting heart rate with the difference in means. Our statistical model is constant over resting heart rate. But we can see from the plot that resting heart rate clearly is predictive of finishing time. And so linear regression is one simple way. It's a straightforward way that we can condition on resting heart rate and use that information to estimate the SATE better. So how is linear regression going to work? Now we're bringing in information from resting heart rate, which I'm abbreviating as RHR. So I'm going to fit a linear regression, and I can plug in my predictions from this regression to my missing Y zeros. So for the first runner, row 1, we observe a Y1 time of 157, and we can impute this value right here. And I can also fill in a Y1 value and get some predictions from that too. And then I can write down my my estimated SATE, my estimated average treatment effect. And the estimate looks very, very similar to the true average treatment effect. But when I calculate the uncertainty is much, much smaller. So my uncertainty intervals are a little bit smaller, and that's more efficient. So now if I was a frequentist, I would be able to reject the null hypothesis that the SATE is equal to 0 in favor of the alternative, that the SATE is not 0. And if I'm a Bayesian, I can make a claim with confidence that that the SATE is less than 0, and hypershoes on average are effective. Now, why did this work? Well, the efficiency got smaller because now I'm using information from resting heart rate. This regression here is soaking up some of the variation, and that is giving me more precision when I'm looking at SATE. Now, something that's worth discussing is it's not, Friedman made a claim in 2008 that it's not universally true that linear regression, even when it's misspecified, is going to give us more precision. And I should go back and say, this model, it's still really misspecified. We're still not accurately modeling the response surface, but because this is a randomized study and we have balance between the groups, it's going to be okay, is kind of the conventional wisdom. That we can get away with model misspecification because of properties of randomization. Now, Friedman pointed out this is not necessarily true. And then properties of randomization don't fix model misspecification, and the parametric assumptions of linear regression are still relevant. And specifically, they can worsen asymptotic precision, and it becomes an inconsistent estimator. There have been some responses, notably Winston Lin in 2013, that with sufficiently large sample sizes, these problems are small and can easily be solved. So generally speaking, the advice is using linear regression to kind of regress out some of the variation is okay, even if those parametric assumptions aren't fully satisfied. Things get much more complicated when we move to thinking about observational studies. So randomized studies aren't always feasible. Why is that? Well, suppose that professional runners are really invested in finishing as quickly as possible, and they think that this new shoe can give them an edge. They're not going to agree to enroll in a randomized study where they know that there's some probability that they may be put at a disadvantage. And so very few people would want, particularly professional runners, would want to enroll in such a study. So in a lot of cases, we just aren't able to get the data. And in the social and medical context, it's often really unethical to randomize people to things. It's really important societally to identify the causal effect of, say, education, but it would be considered grossly unethical to randomly determine who gets to go to college and who doesn't. Now, what we can do is we can just let people self-select into groups. So these 150 runners could just decide on their own to wear or to not wear the hypershoes. And we can really lean on statistical modeling to estimate our causal effect. So we're really going to invest in our statistical model when we can't use information from the design. Now, this opens up some issues, notably confounding variables. So a confounding variable is any pre-treatment variable that predicts both the outcome and the treatment. And I want to point out statistical significance cannot be used to identify confounders. You can have confounders that are not statistically significant. That's very easily demonstratable. And so it is not a good idea to run a bunch of univariate regressions and say, hey, if my coefficient is significant for predicting the treatment, and if it's significant for predicting the outcome, that means it's a confounder. If it's not significant, it's not a confounder. There's all sorts of problems that can open up. And what's so nice about randomized studies, and the reason that randomized studies are often presented as the gold standard, is they can't have any confounding variables, because we've made it that nothing can predict the treatment because the treatment is random. So for something to be a confounder, it has to be predictive of both the treatment and the outcome. We can't control what predicts the outcome. And that's why things like linear regression can improve our performance for randomized studies, because we're regressing some of that out. But we can control what predicts the treatment if we use randomization. Now, the problem is we can't always use randomization. So what can we do? Is there a way forward? And we can still estimate average causal effects for observational studies, but this is going to require that we take a massive leap of faith. And this is a truly large leap. If we make now what's called the conditional ignorability assumption, where both of our potential outcomes are independent of Z given X, where X represents any pre-treatment covariate, and Z represents any treatment assignment. X is really any confounder that exists. It is any true confounder, and the conditional ignorability assumption requires that we appropriately condition on all confounders that exist. So X is all of our pre-treatment covariates, and all of the true confounders need to exist in this subset. So we have to have measured and included in the model any confounder that exists. Now, the problem is we don't know what's a confounder. And so we have to assume that we've measured all of them that exist, and then we've appropriately conditioned on them, meaning that any model-based parametric assumptions that we're using to actually do the conditioning are satisfied. So there's the structural piece that we've actually measured all of the things, and then there's the parametric piece that we've appropriately modeled them, we've appropriately weighted them. Now, the challenge is to make this assumption plausible, we need to measure a lot of stuff usually. There could be a lot of confounders, and it seems more believable when we've adjusted for a lot of things. But when we start adjusting for a lot of things, it becomes increasingly hard to satisfy those parametric assumptions. So there's this huge tension where adding more things makes it harder to model, but we need a lot of the things in order for this to have a shot at being true. So here is some data from our observational study. Now, I want to take a second to point a few properties out. For the randomized study, so this is what our world would have looked like if runners self-selected into the groups. Remember, I pointed out that resting heart rate, really predictive of running fast, probably represents some of the better runners. Now, most of those folks down here are in the treatment group. So runners with lower resting heart rate are much more likely to be wearing hypershoe. And over here, the runners that have higher resting heart rates, much more of them are in the control group. They didn't wear hypershoes. And we have already established that resting heart rate is very predictive of the outcome, how fast you finish the marathon. And so this makes us really believe that resting heart rate is a confounder. And I could use some theory also to inform this stuff. Now, again, this example is synthetic, and I've made it, I've designed it to kind of be easy to demonstrate. And so for now, we're going to say this is our only confounder. Now, in practice, that will almost never be the case. Usually there's many. There's some papers that have adjusted for 200 or 300 variables. But for now, let's just play pretend and know that this is the only confounder. So I'm going to say the structural ignorability assumption is satisfied. We've measured all the confounders. And so all that's left is we have to appropriately condition on them. Now, remember, randomized studies have this really nice balance property where those distributions looked similar. And I said if we took it to expectation, they become identical. No longer true for observational studies. Observational studies are not balanced in expectation, and these distributions look noticeably different. And if we look at the means of these distributions, we can see the means are pretty far apart. Runners that wore hypershoes, lower resting heart rate. Runners that didn't wear hypershoes, higher resting heart rate. Now we're going to go back and say, well, what would happen if we used our magical machine? And this is going to allow us to visit a world in which all of our 150 runners ran the same race in the same context, the same time. Literally everything you can imagine is the same. The only difference is that their treatment was flipped. And so if we have, again, true potential outcomes, we can see the true response surface. We can see that it's a non-linear relationship, very non-linear, in fact. I can, for each runner, take the difference between y1 and y0 to calculate an individual treatment effect tau. I can plot all of these individual treatment effects. So this plot, there's 150 points. Each one represents the runner's true individual effect from the hypershoes. If I take the average of all of these, it's going to give me the SATE. The SATE is just the average of all of the individual causal effects in the sample. And it's negative 4.25. Now, this should look a little familiar. The SATE hasn't changed. And that's because the potential outcomes haven't changed. If we look at the CATE, same exact curve. Runners that have a high resting heart rate around 52, 53 and up, hypershoes become iatrogenic. They cause harm. For the really, really fit runners, hypershoes give a really big boost, as low as 10 minutes, which is huge. Now, I want to point out a very important property. The only difference between the randomized study and the observational study here is I've just changed the treatment. And the why we observe, it's just the potential outcome that we actually directly see. So the SATE is the same because all of the Y1s and the Y0s are identical. The only thing I've changed is the treatment Z. And because Y depends on Z and Z depends on Y is also going to have to change. So the only difference between an observational study and a randomized study is the treatment assignment mechanism, the mechanism at which the treatment is assigned. So now we're going to go back to the real world. So now that we know the truth is negative 4.25, the question is, can we recover that truth? Can we actually get that back? So here's our data, all of the data we have, and we'll start with the difference in means again. That worked for randomized studies. So we'll take the average outcome for the controls and use that to fill in all of our missing Y0s. So basically anybody in the treatment group, we don't know what their time would have been without the hypershoe. We're just going to say it's going to be the average of the outcome for the control group. We're going to repeat that for the treatment group too. So anybody that actually ran without hypershoes, we're going to say, well, your time with hypershoes, our best imputation is just going to be the average of those that ran with the shoes. Now, this is a big problem if your groups are really different, because these are fundamentally different people. So we're using really fast people to represent what would happen to people who are not really fast. And so here's where things start to change. So now we have an estimated treatment effect of negative 20 minutes, way bigger than negative 4. So what's going on? We're just reflecting pre-existing differences between the group. And when we calibrate the uncertainty, we can see that our treatment effect, it's very, very biased. We're not covering the truth at all. Our model is just flat out missing. And so we could get a really wrong conclusion here. Like if you're giving this to a stakeholder and you're saying hypershoes will cause you to run 20 minutes faster on average, that is just not reflecting the reality. It's magnitude, it's a big, big, big magnitude error. Okay, so we know that we also expect the difference in means to do kind of poorly, because remember, we're making this huge ignorability assumption that we've adjusted on all the confounders. We know that heart rate is a confounder here, and we haven't adjusted for it. The difference in means isn't adjusting for anything. So the reason this is so bad is because we know that ignorability is not satisfied. That conditional ignorability assumption that we have measured and appropriately adjusted for all the confounders. So we've measured the confounder. So let's condition on it now. So we can use a linear regression to condition on the confounder. And let's see if this improves things. So I'll fit my linear regression. use this to kind of fill in the missing y zeros, do the same thing for our y1s. And so now I have complete observations for everybody. So according to our linear regression, another property of the linear regression here is that the state, we could think of it as the distance between these two lines. So it's saying that the state is still negative, meaning that hypershoes will cause it to run faster, but this distance looks a lot smaller than this distance was. So it seems like we're getting closer. And let's take a look. So our average, it's around negative 0.7 minutes. Let's see what our uncertainty has to say. When we calculate the uncertainty from our model, we're still not covering the truth. So linear regression is still biased here. We're flat out missing the true state, even though we've conditioned on all the confounders. And because this is synthetic, I'm telling you, and you can believe me, we have conditioned on every confounder here, but we're still missing. And this is getting at those parametric assumption pieces. It's not just that we've conditioned on something, we need to appropriately condition on it. So traditionally, in the 80s, the solution, and a lot of work from basically the 1980s through today is focused on propensity score approaches. There's a propensity score matching and propensity score weighting, and these approaches relax the parametric assumption of linear regression. So remember that for randomized studies, we fit the wrong model. Like we didn't have the correct functional form of the model, but because of those randomization properties, because we have balance in expectation, we could fit the wrong model and still get an unbiased estimate of the state. So the logic of propensity score matching is, or weighting, is we're going to calculate, well, first of all, the propensity score is the probability of getting the treatment given all of the confounders. So it's the probability of z given x. So for a randomized study, like the one we talked about, the propensity score is just 0.5 for everybody. Now, the probability that you're in the treatment is a function of your resting heart rate. So folks with lower resting heart rates have a higher probability of getting the treatment, and folks with higher resting heart rates have a lower probability of getting the treatment. So we can estimate the propensity score with models like a logistic regression. Now, the logistic regression is one way to do it, but there's many other ways. You could use a probit regression. You could use machine learning approaches. You could use all sorts of statistical techniques. And so there's a whole lot of what's called the research degrees of freedom. There's a whole lot of choices that you can make along the way. And let's just for now say we'll use a logistic regression, which is very kind of the traditional thing to do. And once we estimate these propensity scores with our logistic regression, we can use a transformation to get some weights. And so these are called inverse propensity score treatment weighting, IPTW. And so what we're doing here is I'm weighting up people in the control group and people in the treatment group to try to make my observational study look like a randomized one. So after I've done my weighting, if I look at the distributions, the means are really close. Again, remember, when we were just looking at the difference in means in linear regression, those means were still pretty far away. Now that I've re-weighted different people in my control group, I've given a lot more weight to the control folks that have low resting heart rate because we know they're systematically underrepresented. And I've given a ton of weight to this person. This is somebody with a high resting heart rate that just happened to wear hypershoes, and I'm really weighting them up to counteract for all of the folks down here that are in the control group. And so what we can see is the balance in means looks to be a lot better, but there's an important property about balance that I really want to cement. When people think about propensity scores, a lot of folks usually use means to compare how their propensity score model is doing. Balance is not just about means. It's about every single moment of the distribution. And we'll talk about that a little bit. So let's fit some regressions on our weighted data. And the whole idea is even though we're using the wrong outcome model, because we've tried to recover some balance, we're trying to make it like it's a randomized study again. We're going to change the structure of our data to make it resemble a randomized study, and then we can get away with fitting the wrong model. So we'll do that, fit our regression. We've now filled in our missing y zeros and our missing y1s. Now our estimated state looks a whole lot like linear regression. And when we add in the uncertainty, we're still biased. So propensity score weighting did not fix the appropriate conditioning problem. So what happened? So what happened again, this is a balance problem. Even though the means are really similar, these distributions still look very, very different. They have very different variants. If we had more variables, they could have radically different covariants. We need to assume that these distributions are identical. And so if there's still imbalance in variance and covariance in any moment of the distribution, the propensity score model could still be biased. So what are the key points we've covered so far? Both the difference in means and linear regression, they were unbiased estimators of the state, but linear regression was more efficient than the difference in means because we were able to explain some of the variation in the outcome that was explained by resting heart rate. For observational studies, it's different stories. The difference in means was a biased estimator of state, and this is because the conditional ignorability assumption was violated. We did not adjust for any confounders at all, and we know there's confounders. Linear regression was also biased, even though we conditioned in all the confounding variables. So even if we include all the confounders, we need to appropriately condition on. We need to appropriately condition on all those confounders. And propensity score weighting, IPTW, it did not fix the violations of the parametric assumptions. And that's because there was still imbalance. There's still imbalance left over. We have to balance every moment of the distribution, not just the means. And that is a critically important step. So the question is this the best we can do? Are we forced to just really, really try to create balance with our propensity score model, or is there another path? And so I'm going to be talking about another option, which is machine learning for causal inference. Now, there's a lot of different machine learning algorithms. Today, I'm going to be focusing on methods that are based on what's called the regression tree. So before we get into the fancy machine learning models, we're going to start with the building blocks. So the idea of a regression tree is it's a non-parametric way to model data. So this is some clearly non-linear data we have, X and Y. And the idea of a regression tree is if I could just make one cut, if I could just cut this data by one variable at one level and split it into two groups and make my predictions the mean of each group, what would the best cut point be? So we could think of regression trees as actually an extension of ANOVA, analysis of variance, where ANOVA usually have categorical predictors. Here we have a continuous variable, and we're trying to make it into the best categorical variable we can. We're trying to make cuts that explain the most variation in the outcome. So our first cut is going to be at X of 2.7. So if your X is larger than 2.7, your prediction is going to be, it's going to be 2.785. Your prediction is just the mean of this group over here. And if your X is less than 2.73, we're just going to take the mean of all these points. That's going to be 10.38, and that's the prediction. Now, this is not a good predictive model, but we can keep adding more cuts. So the idea of a regression tree is we can keep making smaller and smaller partitions of the data. We're just dividing it into smaller and smaller subgroups, and each subgroup, its prediction is just the mean. So we're going to make more cuts. So after our first cut, once we make our first cut, that has to stay the same. So given that partition, what's the next best cut we could make? And it turns out the next best cut we could make is 0.56. So we're going to make a cut right here. And now we have three groups. And these groups, they're called leafs or terminal nodes. And our prediction is just going to be the average of each terminal node. And we can keep cutting and cutting and cutting. So here is a more thought out regression tree. So if we fit a regression tree to our data, it looks like we're starting to model a little bit better, but there's a lot of stuff to be gained. A single regression tree is non-parametric, but a single regression tree, it's still not very flexible. And we can add more leaf nodes. So we can add more leaves to make it more and more and more flexible, fit the data better and better and better. But then we start really overfitting. So there's this tension where regression trees, they're either going to really overfit or really underfit. And the solution is we can combine a whole bunch of really, really weak trees together to improve predictive performance. So there's several machine learning models that do this. They're called ensemble-based methods. One ensemble-based method is Bayesian additive regression trees. And it's a flexible non-parametric machine learning model. And it's a sum of many, many trees. Here's the whole model where T1 is a given regression tree and M1 are the terminal leaves in that regression tree. And then we have T2 all the way to Tm, where M is the number of trees, and each tree is contributing a little tiny bit. We're going to sum together all their contributions to get a prediction. It's estimated with MCMC draws from a posterior distribution. That's the Bayesian part. And the difference is instead of using hyperparameters like a learning rate or tree depth, we're going to use a Bayesian prior that's going to learn those things for us. So we're using priors to regularize instead of explicit tuned hyperparameters. And we're going to work with an M of 75. And I should say this was developed by Chipman, George, and McCulloch, not for causal inference, just for a standard prediction model. And in their initial paper, Chipman, George, and McCulloch, they basically compared what they called a bake-off, where they had 42 data sets. From these data sets, they generated 840 different trained test splits. And for all of the non-BART models, they tried all the state-of-the-art machine learning models at the time, and they fully tuned them. They tuned all their hyperparameters to make them as good as they could be, and they didn't tune BART at all. They used off-the-shelf default settings. And default BART performed equally well to all of the other machine learning models that have been fully optimized. And it turns out when you optimize some of the hyperparameters that BART does have, some of the prior specifications, and I'm not going to talk about the full prior, that's a content for a different talk, but BART gets even better. So if you do cross-validate BART, its performance is better than its competitors, but if you just use it out of the box, its performance is equal. And so the takeaway, why BART is really going to be helpful to us is we don't rely on extensive tuning. And when it's tuned, we can get even more performance. Also, aspects of the Bayesian piece, like embedding it into a likelihood framework, is going to be really helpful when we want to eventually calculate uncertainty. So Jennifer Hill in 2011 was the first person to propose using machine learning for causal inference. And so what we're going to do is we're going to take our data and we're going to train a BART model on our data set. So we're going to train our model on our data set just as is. This is all of our data. We're going to put it into a BART model. So we're putting resting heart rate and the treatment as our predictors, and we're going to train it on the observed outcome. Now, an important step here, we are assuming that this conditional ignorability assumption is satisfied. BART is not going to fix this. We have to assume that we've measured all the confounders. So once we've trained this BART model, we can look at runner one. This is the first runner in our data set. They happen to not wear hypershoes. So we know what their Y value is. We know that they had a Y0 of 166. Yeah, okay. And so then what we're going to do is we're going to use our BART model to get predictions of what would have happened to this person if their treatment was different. So what would have happened to this person if their treatment was different? And it's going to be a distribution, and that's the Bayesian piece. We get a whole distribution of predictions. Looking at a different runner, this person happened to be in the treatment group. We've got they ran in 160 minutes, and we can flip their Z around, basically keep everything the same and say, hey, what if they ran the race without hypershoes? And we're going to use our BART model to estimate what would have happened, and we get a whole distribution. And so we can do that for every single runner. And let's explore how this would work. So for randomized studies, we can do the same thing we've been doing, but the only difference is now we're really flexibly fitting the response. So before, our difference in means model and our linear regression, they were really misspecified. But now we're really fitting the data cleanly. Now our estimate looks similar to linear regression. But when we think about the uncertainty, we have much less uncertainty. So by really accurately modeling the response in an RCT, we're really reducing the uncertainty and can get more precise estimates of the sample average treatment effect. Now, we haven't talked a lot about Kate up until this point, but an important thing to show is linear regression, the difference in means, they assume the treatment effect's the same for everybody. BART does not do that. So the black line is the true Kate. And these purple bars are BART's estimates of the treatment effect for each person. And so we can see for each individual, we're really estimating the Kate well. So we can actually identify that people with high resting heart rates, the shoe's not good for them, but people with low resting heart rates, the shoe is really valuable. Now, in the observational study space, we can fit our BART model. Again, notice that here, the parametric, BART is non-parametric. So we're not really misspecifying our model. We're fitting the data very smoothly. And this is really aligning with the true functional form. So if we properly model the response, there's no need to do extensive weighting procedures. Remember, propensity score matching, it's just trying to get balance so we can fit the wrong model on the outcome. But if we can just fit the right model on the outcome, we don't need to worry about it. And so that's the logic of BART for observational studies. We're really just trying to flexibly model the outcome. And if that's true, we don't need to worry about making our observational study look like a randomized study. We're not trying to restructure our data. We're just trying to really properly predict counterfactuals. And again, even in the observational study space, we're getting a really, really nice estimate of variation in the treatment effect across X. So this heterogeneity, we're still capturing in the observational space. Now, this example, it was maybe a little bit simplified. There's a whole bunch of scholarly literature supporting evidence of BART's improved performance. You can read these citations for more information. So all of these things is BART for causal inference. It's embedded in the BART cause package. And it makes some assumptions about usability. So to use BART cause, you need to understand structural assumptions of causal inference. You need some foundations in the Bayesian inferential framework, and you need a working knowledge of R. Now, these structural assumptions still exist. BART doesn't fix them, notably the conditional ignorability. So for randomized studies, we have the normal ignorability assumption. And for observational studies, we need to know that we've measured all the confounders. We need to assume that we have. All confounders need to be measured and included in the BART model. Both of those things need to be true. If we've measured them and don't include in the model, it's not going to help us. We make some other structural assumptions like overlap. These are consistent to all causal inference methods in some way or another. And we also make an assumption about SITVA again. Those two things are always going to be there, not the focus of today's talk. Now, despite these structural assumptions, there's a really big hidden assumption. So the hidden assumption to all of this is that people are actually using methods as they're intended. So BART cause, it's a great R package that implements Bayesian additive regression trees for causal inference and all the nice properties we've been talking about. But it turns out a lot of things could go wrong. So we've seen a lot of people not including all of the measured pretreatment variables in the model, not estimating the appropriate causal S-demand, and also just dealing with programming difficulties. You need to have a ability to learn how to use new packages in R, which is not always straightforward. Documentation is generally not great. There's not a lot of resources out there to learn new skills in this space. So to point this out, we're going to look at a slightly more realistic observational study. So imagine we want to estimate the sample average treatment effect, but only for the treated people, similar to the SATE, but a little bit different, of a preschool program. So we have this preschool program, that's the treatment. Our outcome of interest is scores on a verbal reasoning test, and the treatment variable Z, it's not randomized. So our treatment's not randomized, and what that means is there could be a lot of confounders. Now, we've measured 58 pre-treatment covariates. So this is a more realistic setting where we've measured a whole lot of things and need to appropriately condition on them. So if you would like to use BART cause, this is how you would have to analyze this data. So you'd have to load in your data from some CSV or file on your computer. And there's a step where you have to kind of gather all of your confounders together. And you have to make it a specific type of data. So BART cause only takes a matrix or a data frame. It doesn't like other types of objects. So you have to kind of wrangle all of this data together. You'll notice I have a whole bunch of stuff in this big X object I've created. I'm putting in all 58 pre-treatment variables. Why that is, I have no idea which ones are confounders. I can come up with reasons for all of them being a confounder. And if any one of them is a confounder and I don't include it in the model, I'm exposed to bias. My assumption is no longer true. Now, I've seen a lot of people being very anxious about including all of these things, concerns of things like collinearity or model saturation. So because of the Bayesian priors in BART, BART is going to regularize and prevent us from overfitting. So putting in a whole lot of variables is not going to be an issue for it. It's going to appropriately regularize them. And so then we have to put things into the actual BART cause call. It looks a little bit different than a linear regression, few different arguments. If you're only used to kind of using things like LM and R, this would be kind of a struggle. And then you also have to specify a particular target. And so these are all things that are non-intuitive and take a lot of expertise in working with R to understand. If we do that, it'll spit out an average treatment effect, but it's very, very contingent that the implementation is as its creators intended it. So as kind of a way to work on these things, our team has developed Think Causal, which is a point-and-click application for doing and learning about causal inference. So because I'm mindful of time, I may not have time to do the whole demonstration, but you can do start to finish data analysis using Think Causal. And so I can load in some data. Let me find my data set. What? Oh yeah, there we go, causal data. So I can load in my data set, boom, no programming required. I can move along through kind of a causal inference process. It's going to ask me what my outcome is. My outcome's Y. It's going to ask me what my treatment is. My treatment Z. It's going to ask me some information about my study. Here's all my confounders. It's going to provide some nudges. And if you make some mistakes, it'll throw you some warnings. So if I didn't include all of these things, a big warning would pop up and say, hey, are you sure you want to do this? And so the whole idea is we're embedding a lot of concrete help along the way. So if you don't know a question, you can refer to the kind of built-in documentation that'll instantaneously pull up recommendations. And if you really want to learn more, we have a whole library of learning modules that will provide more in-depth explanations about these things. I want to point out too, this is a totally free and open source data set. If you want to do some data cleaning, like maybe rename some variables, you can do all of that on the fly too. So I'm just renaming some of these to get the point across. So there's a whole bunch of data wrangling. It's going to check for missingness. It's going to give you warnings if you have a ton of missing data. So we've really developed a tool where you can do all of these things without any prior knowledge of R. All of this does not assume any knowledge of R. There's a whole plotting apparatus. You could do exploratory data analysis. Like I said, there's some other assumptions that I didn't get too much into. So we can do things like check the overlap. It's going to help us kind of pick an estimate if you don't know it. And so all of this, it's going to provide a scaffolded tool for working with BART cause. And you can go all the way through where it'll spit out a treatment effect and a coinciding interpretation of that. Now, what I want to close with is there's a need to think, do our tools actually make the difference we want them to make? And so recently we've just wrapped up a randomized study where we've evaluated Think Causal. So what we did is we had a bunch of graduate students and alumni come into our lab. We had them estimate the sample average treatment of the treated. So we told them, hey, we want you to estimate this specific estimate for this variable and this treatment. And we randomly assigned them into 3 arms. They either used Think Causal, BART cause, or they chose their own method altogether. We block based on proficiency in R. So if you were proficient in R, you could be in all 3 arms. If you were not proficient in R, you either use Think Causal or you chose your own method. So we only gave BART cause to people that had some proficiency in R. Among people that chose their own method, most folks using linear regression or propensity score matching. So those are kind of the 2 most common approaches by people who were kind of picked their own path. We measured sociodemographic information, some background statistics knowledge, and the outcomes you're really interested in is how well was the estimation going? And so what we found is if we look at distance between the estimate and the true SAT, Think Causal is much, much closer. So here, lower is better. we ideally want 0, and think causal is very close to 0. Now, this is standard deviation units on the outcome. So BART cause and think causal are almost 0.2 standard deviations away from the true set. And when we when we look at these things a little bit more formally, we see that think causal is notably different than folks that chose their own intervention. It is also different than BART cause, but BART cause is not giving us any value. It's performing equally well. It's performing equally well to people that that chose their own method. Looking at percent of intervals that covered the state, here we want higher. We see that about 80% of think causal, actually no, about 90% of think causal users cover the state, whereas only about 20% of BART cause and choose your own adventure users did. Again, BART cause, about a 75% increase, or sorry, think causal is a 75% increase over choosing your own method and using BART cause. And so what these things show is the scaffolded approach makes a really big difference. Like the method alone isn't enough, and it needs to be put in an accessible framework so that it can be used as intended. I want to close by thanking my fantastic collaborators with a particular focus on Jennifer Hill and Vince Story. Whose help has been invaluable to all of this. But it is very much a team effort, and yeah, many thanks to all of my fantastic collaborators. I know we probably don't have time for questions, but
well,
thank you, everyone.
We have time to thank you. So
Yeah.
I'll tap to everybody and thank you for the talk. And yeah, we're a little low on time, so it might be best in the interest of ending right on time for folks to maybe connect with George and other members of the Think Causal team over email to follow up. Thank you everybody for attending. I believe this is our last PRIISM seminar of the spring semester. And so we hope to see many of you in the fall for another exciting series of seminar presentations. So thanks everybody.
Yeah, I just put my email in the chat if people have specific questions.